Logarithmic functions. Solving exponential functions. Consider 2 to the x equal to 10. We know that 2 cubed equals 8 and 2 to the 4th is 16. So it is clear that x must be some value between 3 and 4. And we can use the inverse of an exponential function, namely the logarithmic function, to find that exact value of x. Now recall when we were working with exponential functions and learning the ropes with them, the graph of f of x equal to 2x. We looked at all our different x values and we were able to get this red graph over here to the right. So if I wanted to make a table and graph the inverse of this function, remember when we're doing inverse, we're switching those x's and y's. And so remember with this, it's a matter of we are going to switch the domain and range. So if I take all these values and just start switching them out, and I'll write them here below in my g of x function, that means my x value of 1/8 comes from negative 3. My x value of 1/4 would output negative 2. And I'm just taking all the numbers from above and changing them up or switching my domain and my range. Uh-oh, I had a wrong value there. Hope they didn't throw you. So it gives me negative 1, 0, 1, 2, and 3. And so when I switch those and I graph that, so let's just kind of graph these values. So let's see, at x equal to 1/8, I have a negative 3. At x equal to 1/4, I have a negative 2. X equal to 1/2, I'm now at negative 1. 1, I'm at 0. 2, I'm at 1. 4, I'm at 2. And then over here at 8, I'm at about 3. So you can see this is what this graph is starting to look like. Now this fits into our parameters of our inverse because remember we also learned that the inverse function is reflected over that line y equal to x. And so our domain originally was all real numbers. We could plug everything into there, but our range just came between 0 and infinity. So that means when it flips, our domain is now 0 to infinity. You can see we don't have any x values over there to the left of the line y equals x. And then our range would now be all real numbers. And so we know this function up here, the red function, is y equal to 2x. But what is this function down here? This is actually y equal to log base 2 of x. So we're going to pick up this new idea of log, and I have it written nicely here. This is known as a logarithmic function. You can see that it's written as log. This is known as the base of 2 and then x. Now, we're going to talk more about that, but let me show you two of the basic ones, and both of these are on your calculator as well, and you've probably seen these buttons before. You have common and natural logs. The common log has a base of 10, and so it would be written as log. When we say base of 10, there's a tiny little 10 here of x, or you would just see it as log of x. There's an assumed 10 there. Now, if you want to go into your calculator, I told you that button does exist. So just like when you work with other letters that you type in, there's a couple ways that you can do this. You can either, one, use your keyboard to your calculator, keyboard to your computer, and type in LOG. Two, you can use the ABC here and use the on-screen keyboard and do LOG and then in parentheses. Or you can hit your function button and you can use log that's already written. It's going to auto give you the open parentheses. And so we were just talking about the value of 3. And you can see that that gave me a value of 0.477. So I'm going to take that value of 0.477 and I can just move on into my next calculation. So we can come back here, looking at log of 3 and using our calculator like we just saw. This would also be the same as it was written as log base 10 of 3, but we saw that gave us a value of 4.77. The other type of log that you're going to encounter that's very common is your natural log, which has a base e. Now you will see it either written as log base e of x, or most commonly you'll see it as ln x. And you'll see me write ln in cursive. I always kind of write in cursive like that so it doesn't look like a 1n. But this ln x and this log x without writing those bases, those are the two you're going to encounter the most in the formatting you're going to see. Now this is also a button on your calculator. Let me show you what that looks like. So what you can use is you can either on your computer keyboard type in ln, to go to your ABC and type in ln, or you can hit the function button and use the button ln. You can see it's going to auto give you that parentheses. We want to know what the ln of 500 is, so I'll just type in ln of 500. You can see that that gives me a value of 6.2146. So if I wanted to round that to 3 decimal places, 6.215. Now these are the only two logs that you can enter into this scientific calculator, which is the only calculator we will use for this course. Let's go back and write that down. So this gives me what we saw earlier of point. So this gives me what we saw earlier, 0.477. And again, this does represent log base e of 500, but you're going to see it written like this the most, and this would be our answer rounded to 3 decimal places. Now, what are we going to do with all that? So that gave us exposure, showed us what the formatting would look like. Let's get into the details of what is this log function. The logarithmic base b function is the inverse of an exponential function base b, and that's what we saw earlier. You can see that the logarithm base b and the exponential function base b, we're using the same terminology. And so what we want to be able to do is we want to be able to look at an exponential, so we'll be looking at something like this. Base b raised to the a equal to c, and be able to transform it back and forth and turn it into a log. Notice log also has the base b, like the base of the exponential, of c equal to a. So these a, b's, and c's are meaning the same numbers. C is always going to be greater than 0, and b is not going to be equal to 1. And so this would be a logarithm is equal to an exponent. You can see that this entire log here was equal to a, our exponent, and you can see that over here as well. And what we want to be able to do is take this back and forth. So I'm going to show you a little trick. Super technical. It's called the Snell method. And what you can do is kind of just circle your base and then snell it around. And this will tell you the order in which you want to write your log. Again, it always starts with the base. And then you can see because of the Snell method, you went to your C next. And so that's why C is written here. And then you went up and landed at A. So A would go in that last spot. Now the Snell method works really nice back and forth because not only does it give you from an exponential to a log, but you can start with your log and say, okay, I need to write this log as an exponential. So you start with your base, you snell it around. So that means base B would start first because I'm trying to go this direction back to that exponential. Loops up to A, so that's the next thing you would write down, and then lands on C, so that's the last thing you'll write down. That's really confusing with all these A, B's, and C's, but let me kind of appeal to your logical side and show you how it works with these different numbers. So some basic examples, and you'll see this within your homework, quizzes, and exams. Write the exponential equation as a log. We're not solving, we're just rewriting. And so when we are going from an exponential to a log, you can use the Snell method. Now I know that this is going to be log. This is kind of my template. This is what it's going to look like. And that Snell method can help me because I'm going to start with my base. I'm going to go to 32, and then I'm going to land lastly at that 5. So it tells me I'm going to start with my 2, go to my 32, and then land at 5. And so that gave me what that logarithm was supposed to look like. Again, we're not solving, we're just rearranging and rewriting. Let's do it again. Now this is 3 different pieces you're going to grab. So I'm wanting to write this as log of something equal to something. I've got my 3 spots. I'm not really sure where these go. Well, that's where I'm going to use my Snell method. So I'm going to start with my base, and it would be written here. Then I'm going to move to the next number, and it would go here. And then I'm going to land, lastly, it kind of makes a snail shell. That's what we kind of call it, super technical Snell method. Lands on your -4. So that means that would be written as log base 10 of 1 over 10,000 equal to -4. Now, if you look at these starting values here, like this logically, 2 to the 5th equals 32, yes, that's a statement I recognize. 10 to the -4, that equals 1 over 10,000. Rewriting as these logs, I know, does not feel natural. Like that's not something you've done before. So we're starting to kind of play with this property on how we can change it up, and then we'll be using it in later sections. Let's go on to the next part. Write the logarithmic equations as exponential equations. So now we're going from log to exponential, hoping that it'll kind of change it up. And this is where you're going to kind of see those logical pieces come about. Again, we're not trying to solve for x. We're just trying to figure out another way to write this and be equivalent. So I'm going to use my Snell method, and that's just going to tell me how I'm going to fill in these boxes. So I start with a 2, I'm going to loop to 3, and then I'm going to land at 8. So it would be 2 to the 3rd equal to 8. And logically, that makes sense to me because I'm like, oh yeah, 2 cubed, that definitely is 8. I can do it again. So I'm going to start with 6. I'm going to raise it to the 1/2 equal to, and then I'll land at this last piece, square root of 6. And again, logically, that makes sense. That's a rewrite. That's how I can rewrite that square root. ln x equal to 1. Well, remember, ln x could also be written as log base e of x equal to 1. Well, Snell method works on that as well. So you start with your e, go over to your next number, so that's to the 1st power, equal to your last one, which is x. So these are just rewriting, in our case, from a log to an exponential. Now, this is going to be helpful for us because let's look at these next problems here. It says, solving the logs without using a calculator. And so what I'm going to do is I'm going to rewrite these as exponentials and see if that helps me. Now, typically, this is going to be nice if you have this equal to your value over here to the right. So if you're ever working with a log, first of all, I'm going to look at that. I'm going to say, that's base 4. I cannot plug that into my on-screen calculator. I can only do base 10, base E, or when they don't have those written there. So if you can't work it with that and we're wanting to solve, then try to turn it into an exponential and go from there. So, okay, let me take 4. That would be 4 raised to the y equal to 64. Well, then from there I could think, okay, how do I turn a 4 to the y into 64? Well, I'll just leave 4y alone, but on my on-screen calculator, I could just say, what's 4 to the 1st? Well, that's 4. What's 4 squared? That's 16. But 4 cubed is equal to 64. So I could say, well, that means y would be 3, because that's the only difference between that left and right. And so you really have to get your mindset in that mode of, I'm working with exponentials. Think exponents, not just add, subtract, multiply, divide. Exponents. Let's do another one. So I'm trying to solve for y, and again, this is going to be really nice if I just have this y over here on the right side. So I'm going to start with 121. I can't plug that in my calculator, and I've got to solve this. Well, it does say without a calculator, so I should have another way. So I'm going to Snell it. That gives me 121 to the y, and then land that back at 11. Well, I'm not really sure what to do with that. How do I get a really big number into a smaller number? Well, let's think about this. What could I do to 121? Well, I know square root of 121 is 11. So I'm trying to figure out this unknown, and the square root of it's 11. So that means 121 raised to the 1/2 power gave me 11. So that means y was a 1/2, because remember, radicals are that 1/2 power. Let's look at this next one. And again, this is going to be a little bit nicer if I have that on the right. So I'll say 3 raised to the y is equal to this grouping. And then what I'm going to do is I'm going to kind of manipulate that right side. I'm going to say, okay, well, I don't know what my y is, but I do know, trying to get everything to look the same. What's a 27? That's a 3 cubed. By rules of exponents, if I bump that up to the top, that gives me a negative exponent. And then I said 3 to some power gave me 3 to y power gives me 3 to the negative 3. So that means that y should have been a negative 3. Let's do this last one over here on the side of the page. So again, I like to have my y over here so I can snail around. So I'll say 2 raised to some power would be equal to 1 over 32. And then I'm going to start manipulating, trying to look at what these pieces are. So I'm trying to figure out what y is. That would give me 1 over 32. So I think, okay, 32. What power would give me 32? 2 to the 5th would do that. Again, rules of exponent, I could bring that up. So it gives me 2 to the negative 5. So, oh, okay. So y is negative 5. So that's really nice how that's working out. I was able to take a log. I could not plug any of these in the calculator. So I said, well, let me change it up. Let me try something else. Now, other things that are going to be really helpful for us is going to be some basic properties of logs. And these are going to be the same for natural logs, so we'll write them out to the side as well. Log base b of 1 is equal to 0, meaning no matter what the base may be, log of 1 is always going to be 0. And that's a really nice property, really quick question that you can answer. The same is true for natural logs, so ln of 1 is 0. And I could just check that on my calculator. Now, how does that work? Well, that works because if I snailed this around, that would tell me b to some power would equal 1, and we know b to the 0 power, anything to the 0 power is 1. And we're using a generic b because it doesn't matter. So if I have log of 1, it's always going to be 0. Really quick question to know. Log base b of b, whenever these two numbers are the same, that answer is just going to be 1. The same is true when you have ln of e. That's going to be equal to 1. Now that one looks a little bit different because remember that's log base e of e. And so that's how that one comes about. And I typically remember that because you see how I kind of wrote it messily in cursive. And this kind of looks like O-N-E, like the number 1. So that's also how I kind of remember that. Again, that one is one you could plug in. But if you had done that Snell method, that would say, okay, b raised to what power would give me b? And we know b to the first is just 1. Now next, let's look at something called the inverse property, and this is really going to save us in future problems. If these two are the same, what happens is this whole piece cancels and just gives you x, what was in that exponent. The same is true for your natural logs. If you have ln e to the x, that's just going to be x because this would cancel. I always say it kind of looks like O-N-E, like we just said, or 1. Or sometimes if I write it real fast, it looks like the word L-I-N-E, like I could put a line through it. Then other part of an inverse property kind of does it in reverse. If I have b as my base, and then that whole log base b of x is in the exponent, the fact that these two are touching kind of cancels each other and just gives you x. As a natural log, it would say e to the ln x. Again, this e's and ln's being beside each other just gives you x. And knowing these properties and how logs work can really save you in a problem or help you. In the next one, I can do 8 problems really quickly based off these basic properties. I'm just going to apply everything we saw. So log base 4 of 1, that's just 0. Log of 1 is always 0. ln of 1, that's 0. Again, log of 1 is always 0. Log base square root of 7, square root of 7. Since these are the same, that's just 1. ln, just 1 again. Log base 4 of 4 to the 5th. These essentially kind of cancel each other out with that inverse property, so it just gives me 5. ln just cancels, gives me 15. The number 4 is your inverse property again, so this would cancel to give you 20, and this would cancel to give you 7. These are really nice problems. You're going to see them on the homework because they're very quick foundational properties that we're going to use as we move forward. Now the next one we're going to look at is known as the one-to-one property. This one must have a single log on each side. And it says if you have a log equal to log and the bases are the same, then what you can do is just set what you were logging equal to each other. And so that's going to be really nice in solving problems like this. You can see that this was log 3 and this was log 3. So I can just set x equal to 12. So I solved for x. And I want to do some simple problems. I want to err to your logical side so you can see how these pieces are coming about. And then we can apply that to some more complicated situations. ln x is equal to ln 4. So that just means what was x? It was equal to 4. This is that one-to-one property. Next one says log base. This is log 2x plus 1 equal to log 3x. Remember, that's an assumed base 10. So that means the bases would be the same. So I could just say 2x plus 1 is equal to 3x. And I could solve this out. And that gives me 1 equal to 1x. And you can see my solving, not a big deal, but based off the one-to-one property, I was able to do that. The same is true with your natural logs. I'm taking the natural log of something I don't know plus 3 equal to natural log of 7. Therefore, x plus 3 is equal to 7. Subtract it over, and I get x to be 4. The last one here looks a little bit more complicated, but again, let's apply those foundational skills that we're looking at. Log base 4 of x squared minus 6 equal to log base 4 of 10. Because these are both the same base, they're both log base 4, that means I can just set x squared minus 6 equal to 10. And I can solve it out. So add 6 to both sides. Gives me x squared equal to 16 and square root. So x equal to, don't forget, plus or minus 4. Now when you do get into here, this was just going back to solving your quadratics. Because we do have domain restrictions with our logs, you do want to check to make sure they both work, because we're not going to have any negative issues. And in this one, there's no problems with it because of that squared. Now, what do you need to know from this section? You need to know those basic properties, the one-to-one properties, and how to change an exponential back to a log. That might be something you want to put on a Post-it note to kind of simplify up your notes to help you as you're working through these homeworks. But as always, reach out for assistance.